Good evening, Emma. Welcome.
Good evening. Thank you.
Right. She grew up in Worthing, where she attended Davison Church of England High School for Girls between 1988 and 1992, and Worthing Sixth Form College between 92 and 94. Following her A-levels, she studied for a master's degree in physics with space science and technology at the University of Leicester. That was from 1994 to 98. So following the successful completion of her 4-year degree, she obtained a PhD place and began studying the magnetosphere of Jupiter under the excellent supervision and guidance of Professor Stan Cowley. She was awarded her PhD in 2001 for her thesis entitled Large-Scale Current Systems in the Jovian Magnetosphere. In 2003, she was awarded a PARC postdoctoral fellowship to study Saturn's magnetosphere. She was then appointed to the department's lecturing staff in 2005 and have enjoyed teaching undergraduates ever since. In 2009, she was promoted to reader, and in 2013 was promoted to professor. To date, she's published 120 papers in the scientific literature, and my work has received national and international recognition. She won the Royal Astronomical Society's Prize for Best PhD Thesis in 2002, and the Prix Baron Nicolai Award for Space Physics in 2003, the European Geophysical Union's Young Talents in Geoscience Award in 2005. She gave the RAS Sir Harold Jeffreys Lecture in 2009 and was awarded a Philip Leeuwenhoek Prize for Astronomy and Astrophysics in 2011. In 2018, she won the Royal Astronomical Society's Chapman Medal and regularly gives public talks on the solar system, topics such as Cassini mission to Saturn, oceans, ices and fire, the mysterious moons of Jupiter, and auroral processes in the outer planets. So please all give our Mexborough and Swinton Astronomical way to welcome Professor Emma Bunce.
Oh, thank you so much.
Thank you.
Thank you. Thank you. It's so great to be here this evening. Thank you for inviting me. And of all those talks that you've just mentioned there, Steve, I'm giving none of those tonight. It's something different. So, right, let me first of all share my screen, and then hopefully that will work without a hitch. Let me just give me a moment to organise myself. Okay. Okay, so thank you so much, everyone, for coming along to listen to this talk this evening. You've just heard my life history from Steve there. So yeah, quite a lot been going on over the last few years. So in a nutshell, as you've heard, I'm a planetary scientist at the University of Leicester. Behind me is Jupiter, which is probably one of my favourites in the solar system, but tonight I'm going to be talking to you about Mercury, and I'll go on and explain why that is in just a moment. I'm currently also the head of School of Physics and Astronomy at the moment, which is a 4-year job that I'm doing through a global pandemic. So it's been a busy year, I have to say, and as you can tell from undergraduate, they've just not managed to get rid of me, really. So now I'm actually running the physics department, which is kind of amusing to me, I have to say. And the other logo that you can see on my front slide there is the Royal Astronomical Society, because I'm also the current president of the RAS, which is a very interesting job to be doing in my spare time, whatever that is. So as you've heard, I sort of study a variety of different planets in a number of different ways in our solar system, and obviously I'm not going to have a chance to talk to you about much of that this evening, but my experience is really in studying the Jupiter system, the Saturn system, and more recently, Mercury. So today what I'd like to do is tell you about a new space mission to Mercury, which is called BepiColombo. And I'm actually the principal investigator on one of the science instruments on the BepiColombo mission. And that instrument was designed, developed and built right here in the UK, which is quite exciting. So that's why I'd like to talk to you about Mercury. And I would like to introduce the mission and the instrument that we've built at the University of Leicester, and a little bit about what it's going to tell us about Mercury. So I hope that you will find that interesting. So first of all, I'm just going to dive right in. I'm just organising my screen. Oh, there we go. Got you all at the bottom of my screen now. Perfect. I like to see who I'm talking to as well as talking to the slides. Okay, so I'm just going to go from the very beginning. There we go. So first of all, I just want to talk to you a little bit about Mercury itself. I don't know, I don't like to assume what people know or what people don't know, so I'm just going to start at the beginning. So the diameter of Mercury, as you can see there, the little grey planet in the front, is just under half of that of the Earth. So it's about 4,800 kilometres across, and as I'm sure you all know, it's by far the smallest planet in the solar system, now that Pluto has been demoted from being a planet. And interestingly, two of the, sorry, I have to just get my cursor in the right place so that we advance the slide. Okay, I'm getting there. Two of the moons actually in the outer solar system are bigger than the planet Mercury. So that's quite an interesting fact, which you may or may not know. The first one at the bottom, which I just put onto the slide there, is Jupiter's largest moon, Ganymede. And the top one, so that image at the bottom there is taken from the Galileo spacecraft at Jupiter. And the top sort of collection of images, it's not one image, but the top collection of images comes from the Cassini mission at Saturn, and that moon is Titan. And both of those moons are actually bigger than Mercury, which is a significant fact whichever way you look at it. So we tend to think of the moons in the outer solar system, Jupiter and Saturn, as being planet-sized moons, and I suppose that in the same sense you can think of Mercury as being a moon-sized planet. Mercury is also an inferior planet, and I always say this to my students and say it doesn't mean that it's not as good as the others. It's referring to its location in the solar system. Obviously, if something is following an orbital path between the Earth and the Sun, then it's known as an inferior planet. It's also a rocky planet, as you can well see. Broadly speaking, very broadly speaking, it's similar in makeup to Venus, Earth and Mars, which are collectively known as the terrestrial planets. And I think what's really amazing when you look at the picture of Mercury and the Earth in front of you is the very obvious difference between the objects. Mercury is sort of boring looking. I hope Mercury doesn't mind me saying that. Rocky, cratered, looks a bit like the moon actually, while the Earth is fantastically covered in oceans and landforms and greenery. The atmosphere, you can see clouds in the atmosphere there in that beautiful image. We see geological activity, observations from space, you can see that, and of course teeming with life, which is us discussing these planetary objects here this evening. And I do also note that it is Earth Day, so I'm quite pleased to be showing an image of the Earth today. So they look, despite the fact that they're similar in nature and both terrestrial planets as we would classify them, they're obviously very different, and there's a lot to do with that. A lot of that is to do with Mercury's location in the solar system, of course. So let's just go forward. So I'm having a little bit of trouble changing slides. Here we go. So this is just a quick, a simple diagram. The planet sizes are approximately to scale, but of course the distribution of their locations in the solar system is not to scale. But just to point out there, Mercury, closest planet to the Sun, and it orbits, I would say, fairly treacherously close to the Sun. It's at a distance which is just over a third of the distance between the Sun and the Earth. And the average distance between the Sun and the Earth is known as an astronomical unit, which is 150 million kilometers. And Mercury's average distance from the Sun is 0.4 astronomical units. So it's just over a third of the distance compared to the Earth. And of course, what that means, you know, it has a number of effects, but what that means is that the intensity of the Sun on the surface of Mercury, it varies, but is something like 7 times that compared to the Earth. So one of the interesting things and one of the unknowns about Mercury is it's not particularly clear to us, with the knowledge that we currently have, whether Mercury was formed at that location, at that orbital distance, or if it migrated from elsewhere in the solar system. And there are a number of different ways we can think about that, and I'll come to that later in the talk briefly. But what we do know about Mercury from the history that it tells us by what's present on its surface, and also because of its location so close to the Sun, we know that Mercury has undergone some dramatic events in its past and continues to experience the most extreme conditions in space, so space weather, compared to the other planets in the solar system. So poor old Mercury gets a bit of a battering very close to the Sun. So, of course, being so close to the star at the centre of our solar system is what makes it very challenging to send any spacecraft to visit it. And I will talk to you a little bit about those challenges as we talk about the missions later on in the talk. And as I've already mentioned, the planet orbits at roughly 0.4 astronomical units, so just over a third of the Sun-Earth distance. So as you can see in this picture here, I don't know if you can see my cursor, but obviously this is the sunlit portion of Mercury, and here is the Sun. And the sunlit side of Mercury actually reaches something like 430 degrees Celsius. No great surprise that the surface of Mercury would be very hot, close to the Sun. But what you might find surprising and interesting is that actually the variation between the sunlit side and the dark side, or the night side of the planet, so the bit that's in shadow here, the variation in temperature between those two sides of the planet is actually significant. Now, there's a complicated reason for this, which I'm going to try to explain to you, partly to do with the fact that Mercury is in something called a 3-to-2 spin orbit resonance with the Sun. Okay, so it's very difficult to imagine. I couldn't draw it for you if you paid me, but what I will try to do is explain what it means. Okay, so 3-to-2 spin to orbit resonance. So the spin part refers to the time it takes for Mercury to rotate on its axis. And the orbit, obviously, is the time that it takes for Mercury to travel all the way around the Sun. Okay, so it has a 3-to-2 ratio in the times for those spin and orbit all the way around the Sun. So it means that for every 3 rotations that Mercury makes on its axis, it travels around the Sun exactly twice. And that's the 3-to-2 spin orbit resonance. Doesn't help much, does it, that explanation, in trying to understand what it actually means for the planet. Okay, let me try and explain a little bit more. Mercury rotates really slowly. So as you know, approximately 24 hours for our own planet to rotate on its axis. That defines our day. Mercury rotates every 57 Earth days. Okay, so it takes 57 Earth days to turn on its spin axis once. And because it's very close to the sun, it only takes 88 Earth days to orbit all the way around the sun. Okay, so its year is just 88 Earth days long. So because of this interesting effect, and it's hard to imagine, but it has a very slow rotation and moves around the sun quite quickly. What it means is that if you were standing on the surface of that planet, which would not be recommended at all, a given location on the surface of Mercury would experience sunrise to sunrise in 176 Earth days. So that means it's daylight at a given spot on the surface of the planet for nearly 3 months. And that is partly why the surface temperature is so significant on that sunlit side. Unlike the Earth, as we've already seen, Mercury has no atmosphere, and as I've already mentioned, hence you can see directly the surface of the planet. And so it has this very long daytime, but equally well, the dark side of the planet is also dark for a very long time, and there's no atmosphere that can retain that heat of the daytime. And so the dark side temperature is actually minus 180 degrees Celsius. So that's a pretty surprising fact for Mercury, given its location in the solar system, I think. Now, its rotation axis itself, so its rotation axis is aligned with ecliptic north, unlike our own planet. And so Mercury doesn't experience any seasons like we do due to the tilt of that rotation axis. However, it is on an elliptical, a very elliptical orbit around the sun. So most planets actually are on elliptical orbits around the sun, but Mercury's is really quite elliptical. That means that it gets closer to the sun and warmer during part of the orbit compared to the other part. So I mentioned to you that the average distance was 0.4 astronomical units, but that number actually varies between 0.3 and 0.46, which is a significant difference. Plus and minus 0.08 astronomical units, or in our recognizable numbers, it varies by 12 million kilometers away from that average number. So a significant difference. And that means it experiences hot and cold seasons, or I would say probably a better way of putting it is very hot and slightly less hot seasons for that reason. So due to the ellipticity of its orbit around the sun. So an intriguing question that we have about Mercury is, how did the planet form and evolve, and how has it survived in this location so close to the sun? So I'm going to be talking about how we will try to contribute to answering some of those questions with our new mission. Okay, so another key fact I just want to touch on before we get to our space missions and to tell you about what those missions have found. I'm just going to keep an eye on the time so I don't go on too long. So another key fact or interesting fact about Mercury is that it is actually extremely dense. And this can be measured from observations of the size of the planet and its mass, and you can work out the something called the uncompressed density, or just the density of the planet, and that number shows that it's slightly less dense than Earth but slightly more dense than Venus, so not particularly remarkable perhaps. But an important fact with planets is that you have to take into account the size of Mercury. So because Mercury is very small, it has less internal pressure and hence less self-compression. And you can take that into account and work out something called the uncompressed density of the planet. And if you do that calculation and compare it to the other planets in the solar system, we find that its density, uncompressed density, is higher than any other planet in the solar system. And that's a pretty remarkable fact, and is telling us something important about the interior of the planet. And a reasonable explanation for this is that there could be a significant dense iron core occupying a large fraction, and a larger fraction compared to the other rocky planets. And that's sort of shown in this exploded view of Mercury. And it's actually thought that Mercury has an iron core that takes up something like 75% of its radius, which is significantly more than the other terrestrial planets. So already we know that Mercury is slightly different to the other planets. Okay, so planetary exploration is really what I do in a nutshell. And so I'm always interested in the missions that have been through the solar system to visit the planets, and what we can learn by sending spacecraft to the planet itself. It's difficult to observe Mercury with a telescope, as I'm sure you all well know, because of its proximity to the sun. So if you want to learn lots of details about the physical properties of the planet and how it works, you really need to send a spacecraft actually to visit the planet. And amazingly, this was done for the first time in the 1970s. Actually, the first mission to visit Mercury was called Mariner 10, and this was a NASA mission that did 3 flybys between 1974 and 1975. So Mariner 10, because it was the first, obviously has a lot of the discoveries and the first mission badges that it collected in doing this. So it was the first mission to Mercury. It was also the first mission to perform an interplanetary gravity assist maneuver. So that's when you use the planet itself to change the direction and the velocity of the spacecraft. And actually the mathematics required to make that happen were calculated by an Italian scientist called Giuseppe Colombo. And that's where our new mission, BepiColombo, gets its name from. So he did the calculations that showed that you could use Mercury itself as a gravity assist to change the direction and velocity of little Mariner 10 in the inner solar system, such that it could perform 3 flybys of the planet and gather the first images of the surface and the first information about tiny Mercury. So even just on 3 flybys, Mariner 10 managed to image 40% of the surface, which is pretty impressive, taking some 2,800 images. And it revealed, as you can see here from these images that have been stitched together, it revealed a heavily cratered world, somewhat similar to our moon. But it had some intriguing features from these images, such as smooth plains and large impact basins, and some very interesting deep scarps that were suggesting a dramatic history and evolution of the planet. Mariner 10 also discovered, to everybody's surprise, that Mercury has its own magnetic field. Now, of course, the Earth has its own magnetic field, which is generated deep within the core, but Venus does not, and Mars has the sort of remnants of a magnetic field, but doesn't have a significant magnetic field. So nobody was expecting to find a magnetic field at Mercury, but it does have one. It's very weak. It's about 60 times weaker than our own magnetic field, but it's there nonetheless. And its presence suggests that the interior of Mercury must then contain a molten iron layer in order for that magnetic field to be generated and sustained. Related to that, Mariner 10 also gets the badge for discovering the magnetosphere of Mercury. You heard that word a couple of times during the very kind introduction that was given. So the magnetosphere is the extended magnetic environment around the planet, which contains the planet's magnetic field on the inside and is bounded by the solar wind and the sun's magnetic field on the outside. So it's this sort of bullet-shaped or comet-like shape, actually, magnetosphere, and it is controlled by the magnetic field of the planet on the inside. And then the sun's magnetic field and outflowing plasma, known as the solar wind, shapes the magnetosphere such that as the flow comes from the sun on the left in this picture, it squashes Mercury's magnetic field on one side and stretches it out into a long tail on the other side. So that was a great surprise and really exciting results from Mariner 10. So we already knew from images that there was no significant atmosphere, but Mariner 10 also made some first measurements of a very thin envelope of weakly bound elements that form something called its exosphere, and a variety of elements within that. So those were all very important facts that Mariner 10 discovered, and it also confirmed this high uncompressed density of the planet. Okay, let me just show you a couple more details. So Mariner 10 gave us the first view of something called Chloris Basin, which you may have heard of. It's a significant feature on the surface of Mercury, and it's this feature on the left-hand side here. And you can see it's a large impact crater. Obviously, I've stuck a great big white arrow across it and put some numbers on it. That's just to give you a sense of scale. So it's about 1,500 kilometers across. So if you remember that I told you that Mercury was about 4,800 kilometers across, it's about a third of the diameter of the entire planet. So that's a significant structure on the surface of Mercury. And actually at the edge of this, we now know that there are mountains that are 2 kilometers high that go all the way around the outside of this impact crater. Interestingly, the material that was lifted up during the creation of this impact crater actually had a significant effect on the entire planet. And it's thought that the asteroid that must have created this structure was probably itself 100 kilometers across. So that's a significant impact and may well have had a serious effect on Mercury, and it probably wasn't the only giant impact that took place in Mercury's history. As I say, it had a global impact, and it's thought that if the impact occurred on this side here at the top, that actually the effect of that, surface waves and compression waves going through the planet, actually jumbled up the opposite side, the antipodal point to that impact crater. And you see that on the right-hand side. When this was first seen, the scientists on the team termed it weird terrain because they had no idea what it was and they hadn't seen anything like it before. And it's now thought to be the result of this massive impact crater on the opposite side. So it's thought that the impacts like this, Chloris and other large impact craters on Mercury, may have triggered volcanic activity on the planet. Okay, so I'm going to move on to the next mission. So I hope that isn't going to upset your eyes. Sort of, it's a bit juddery there, isn't it? It's not ideal. It'll stop in a second and I won't play it again. Okay, so the next mission to Mercury is the Messenger mission, another NASA mission. And this was the first spacecraft actually to go into orbit at Mercury. So after its journey into the inner solar system, after multiple flybys, it went into orbit at Mercury for 4 years between 2011 and 2015. And so when it arrived at the planet in 2011 and actually went into orbit around Mercury, it was able to do much more than Mariner 10 because it was now actually hanging around for 4 years staring at the planet, and you can obtain much more information than you can on those flybys. So it obtained incredible high resolution images. This is false color, I'm sure you've realized. This is not the color of Mercury, but it's false color, which enables you to bring out some of the features that you see. And it actually shows variations in spectral reflectance. So it does give us some information about potential variations in composition, what the surface is made of. And it may give information also about how old features are. So in this particular bit where it's stopped, bright sort of pale blue or white features could be young features, and actually the orange that you can see dotted across here is probably lavas where there's been volcanic activity and the surface has been flooded with lavas. And dark blue is something called low reflectance material, which is simply named because nobody actually knows what it is. So that's something that we have yet to understand. But Messenger took 255,000 images of the surface over its mission and managed to obtain a typical surface resolution of 1 kilometre per pixel in the images. So that's not particularly great compared to your mobile phone, but bearing in mind it's a camera on a space mission, those are actually really very high resolution images, and clearly we can do a huge amount with those surface images. So let me just show you a couple of things that we can learn from getting those close-up views of the surface. So Messenger taught us a great deal about the surface terrain, and of course that's one of the main benefits of sending a spacecraft actually to orbit the planet. You get a really nice close-up view. So we've learned that there are smooth planes between craters, and this, I alluded to this from the Mariner 10 discoveries, and that was something that people noticed straight away looked different to other comparing to other bodies. And those are vast regions of the surface which are actually probably relatively young. In geological terms, they're still very old, but relatively young compared to other regions. And you can see, and these are the volcanic plains, so likely to have been flooded with lavas when the planet was volcanically active. And one of the really interesting things you can see is something called ghost craters, which is where you have an impact crater which has been filled with lava up to the top of the impact crater, and you can just about see the outline of that depression in the surface that was previously there. So I don't know I'm not sure if you can see my cursor or not, but I'm just outlining one here, and this is a ghost crater. So you can see the circular, it's right in the center of the image if you can't see my cursor, and that is a ghost crater. So where an impact crater has been flooded with lava in the past, and obviously you can now see those older historic craters underneath that feature. Another thing that we've seen which is pretty unique to Mercury is something called compression folds, and I'm showing this in the central image here. So this is a compression scarp running along the center, and those are actually formed, or thought to have been formed, as Mercury's interior cooled and the planet actually contracted. So its surface then deformed as the planet was contracting and created these sort of wrinkle ridges and lobate scarps, as they're called, that are associated with that compression of the planet. So this particular one here is about 1,000 kilometers long, and the ridge is about 3 kilometers high. So they're sort of like cliff edges. So it would be incredible to see in more detail. So what we can see is that those features, the compression features, sit on top of the other features, such as the craters and the smooth plains. And that tells us something about the order in which those features have occurred. So the oldest features are the impact craters. Then there was a period of volcanic activity, possibly started by the impact craters, and then as the planet has cooled and compressed, that's the final part of the jigsaw. And it's likely that the compression of Mercury actually then shut down the volcanic activity. So as the planet contracts by only a few kilometers, it's not many kilometers, maybe something like 7 kilometers of its radius, that will have shut down the volcanic activity. So that's pretty interesting as well. We also have some interesting results on the right-hand side, which indicate that there is actually, it's thought that there is water ice in the shadowed craters at the pole. So that's pretty surprising. I bet nobody was expecting you'd find ice on Mercury, the planet closest to the sun. It's not at all what you would expect. But actually, because of that 3-to-2 orbit resonance, there's a reason why I had to explain that to you. Some of those craters near the pole are actually permanently shadowed, so they never get that full heat of the sun, and they're always in that dark region. And so it's interesting that some of the data is suggesting that there could be water ice in those craters, something to follow up with BepiColombo. And then on the left-hand side, finally, this is a map of the composition of Mercury's surface, or as we would call it, chemical terrains. taken by an instrument very similar to the one that we have built at Leicester. And the surface is actually shown to be rich in magnesium and sulfur, which is what we would expect, but depleted in aluminium and calcium and iron, strangely enough, which is not necessarily what was expected. What was a real surprise from the MESSENGER mission was the abundance of volatile elements, so elements such as potassium and sodium. And so volatile meaning that if you heat it up, you would expect it to evaporate. So you wouldn't necessarily expect to find those sorts of elements in abundance on a planet that has a surface temperature of 430 degrees Celsius, but actually more than that, a surface which has probably undergone some pretty serious dramatic events like those massive impact craters, which will have taken its surface to much higher temperatures temporarily. So lots of things that still need to be explained about Mercury. Okay, I just want to talk a little bit about what MESSENGER found about Mercury's magnetosphere. So MESSENGER showed that this magnetosphere, which I described briefly before, so just as a reminder, this is a similar sort of picture. We've got the sun on the left and it's blowing the solar wind, carrying the sun's magnetic field towards Mercury from left to right and interacting with Mercury's magnetic field and creating this magnetosphere, so squashing the field on one side and stretching it out onto the night side. And what MESSENGER found is that Mercury's little magnetic field, perhaps unsurprisingly, is very strongly driven by that solar wind. So if the sun is active, then Mercury's magnetosphere is very active. And actually, interestingly, Mercury's magnetosphere shares many characteristics with our own magnetosphere, which we understand very well, but it's like the much more extreme version of events. So it's very dynamic and the timescales are rapid. And of course, Mercury doesn't have an atmosphere, so there are lots of differences as well. But some very interesting results coming from the mission relating to the magnetic field and magnetosphere. One of which is that because that field is so weak, the solar wind can actually push that dayside boundary, so this boundary here, which I'm just outlining, it pushes it almost to the surface of the planet, squashes it so much that it almost gets to the planet. But that very large iron core in the interior then actually plays a role. It then actually induces an electric current within that iron core that creates a little magnetic field which pushes back on the solar wind and magnetic field. So just because of Mercury's interior makeup, this effect was discovered to take place, which is, I think, unique within the solar system. The magnetic field is not symmetric, it's offset or shifted up towards the northern hemisphere by about 20% of the planet's radius, and is a very interesting interaction and space environment. So we learned a great deal from the MESSENGER mission. So those are two really important missions advancing our knowledge of Mercury. But hopefully, as I've just been talking, you'll have seen there are lots of things that we still don't understand, and our next logical step in our exploration of this planet is to send a new mission along to Mercury. And this is where BepiColombo comes in. I just need to keep an eye on the time. Where have I got to? Just move you across a little bit. What time do you want me to stop, Paul?
Don't worry about that. When you're ready to stop, we'll be
you better here. Tell me. I'll just keep going. No, I won't. Sure. I will. I've got my clock visible now, so I will make sure we finish in good time for some questions.
Don't rush.
Okay.
Don't worry.
So the next logical step in our exploration then is to send our new mission, which is very exciting, called BepiColombo. This is a partnership, which is really nice, between the European Space Agency, ESA, and the Japanese Space Agency, JAXA. So we're actually working together in international cooperation, which is really important to talk about, actually. So you can ask me questions about that at the end if you like, but it's incredibly important. We simply could not have done it on our own, you know, for financial reasons and for lots of other reasons, but it's a really good thing that we can have international cooperation in these missions. It just allows you to do so much more. So the mission cost about 1.5 billion euros, and it consists of a 4-ton spacecraft, which you can see in the centre here, the white body of the spacecraft. It's actually 3 modules stuck together. And I think I've got a slide that shows that in a moment, so I'll hold off from talking about that for now. And it was launched, successfully launched in October 2018, which sort of blows my mind. I know we've all lost a year, haven't we? But, you know, we're actually now a significant way through the cruise to Mercury. But as you can see from the start time of the mission, it doesn't arrive at Mercury until 2025. So from the 2018 launch to 2025, that's a 7-year journey to the inner solar system, which I'll talk about in just a moment, because that's a pretty long time. So it's going to be the first 2 spacecraft mission actually at another planet in our solar system. So that is a first for BepiColombo. And there are 2 separate spacecraft, one built by the Japanese Space Agency, one built by the European Space Agency, which carries our instrument, and I'll come back to that very shortly. Okay, here we go. So this is a little bit about its journey into the inner solar system, because you may be thinking, why on earth would it take 7 years to get to Mercury? You know, on the grand scheme of things, it's not really that far away. And if you were thinking that, then you would be absolutely right, because if you were to go on a direct path between the Earth and Mercury, straight line, make a beeline for Mercury, it would take about 3 months to get there. Trouble is that if you did that, the strong gravitational pull of the sun at the centre of the solar system would just accelerate the spacecraft straight towards the sun, and that would be the end of your mission. You would have absolutely no chance of slowing down enough to capture into orbit at Mercury. So in order to achieve orbit at Mercury, we have to take this really long and circuitous route in order to fundamentally slow down enough to get into orbit at Mercury when we reach our destination. I was thinking that was going to be a really long 7 years, but as I've just said, it is just flying past. We've got lots of other things to do, and we're also talking to our instrument fairly regularly, and you know, we have things to do, sort of practical things to do on the project side before we start the mission. So in some ways that 7 years is quite helpful. That's the positive way of looking at it. I'm being patient, waiting for the data. So how do we do this slowing down? So there are 2 solutions to this problem. The first is that we use gravity assists, and if you've been watching the little movie Running, then that's what you're seeing. So this is again where you can tap into the orbital angular momentum of a planet itself, and you can use that to speed up your spacecraft, but equally well you can use the planet to slow down the spacecraft. So this is a really clever technique, and it's used all the time in planetary exploration. And so for this mission, we're actually using a series of 9 planetary flybys to help slow down the spacecraft enough that it can be weakly captured into orbit. So we started off with some flybys of the Earth, Venus, and then we've got 6 Mercury flybys until effectively you can think of it as the spacecraft is just about matching the orbital speed of Mercury, and it sort of sneaks up behind and gets captured into orbit around the tiny planet. But actually those gravity assists aren't really quite enough to do the whole job. So Bepi also uses solar electric propulsion to provide thrust throughout part of the journey to Mercury. So it's essentially a set of brakes, which will also help slow the spacecraft down. And so that's what you can see at the back of the spacecraft here, these thrusters. And part of the thrusters were designed by a company called Kinetic in the UK, as well. So there's quite a lot of UK industry involvement in this mission, including Airbus and Kinetic and probably others which I've temporarily forgotten. So that's obviously you know, a really great thing for the UK. So the thrust is actually pretty weak. It's not a huge amount of force that's applied from these thrusters. I think it's, if I remember the numbers correctly, it's about 290 millinewtons, which is not a lot of force at all. But actually, you don't need a huge amount of force, and you don't need a huge amount of force if you apply it over a very long time. And so in total, it'll be about 2 years of those thrusters burning, and that just provides enough to slow the spacecraft down, along with the flybys, to finally allow us to be captured into orbit at Mercury. So it's a pretty efficient system, actually, and the kinetic design was sort of huge, you know, step forward for industry as well. If you're interested in that sort of thing, hopefully that was interesting information. So so then once the spacecraft, so that stack was the thruster module, and it was the 2 spacecraft all kind of stuck together. If you ever want to see the model of this, by the way, if you ever find yourselves in central London, if you go to the Science Museum, you can see the structural thermal model of BepiColombo, which is really worth a visit if you happen to be in. It's free to go into the museum. You can literally walk in, go and have a look, and walk out again. It's really, really good. So if you do happen to be in London, I would recommend that at some point, obviously post-COVID. So, and if you do see that, you'll see our instrument and some little information that we did for the museum, which was quite fun. So when it arrives at Mercury, then it splits into the 2 spacecraft, and we have the European Space Agency spacecraft here, which is the Mercury Planetary Orbiter, or just known as BEPI. And this is the one that our instrument is on, and that is in a slightly elliptical, very close orbit. So it's takes about 2.5 hours to go around that orbit. And it's about 480 kilometers at the closest point from the surface of Mercury, and about 1,500 kilometers at the furthest point. This little spacecraft over here is called MIO, and this is the Japanese spacecraft, and that is in a polar elliptical orbit as well, same as this, but as you can see, the scale of this orbit is somewhat different, and this highly elliptical path is 600 kilometers away from Mercury at the closest point, and 12,000 kilometers at the furthest point. So each one has been designed specifically to answer science questions. That's why the orbits look like they do. This spacecraft is looking at the planet itself, so looking at its surface, studying the interior through measurements of magnetic field and gravitational field, and measuring the exosphere. And then the Japanese spacecraft, which is orbiting further out, I've just put that magnetosphere picture in the background roughly to scale. That spacecraft actually is dedicated to studying that magnetosphere and space environment. So that orbit has been designed specifically so that it samples all the way throughout that magnetosphere, measuring charged particles, measuring magnetic fields, and how the solar wind interacts with the magnetosphere. So the really nice thing about this mission, because you have 2 spacecraft as well, each one has its own job to do, but equally well, if we can put the data together from the 2 spacecraft, we can also learn new things from joining the data together. So we can, for example, we can study emissions coming from the surface, which I'll explain later, and this spacecraft could be sampling what's happening out in the magnetosphere that could be causing something coming from the surface. So that sort of thing is only possible if you have 2 spacecraft. So each spacecraft then has a series of instruments, and I won't go into the details, but there is what we would call a fairly standard set of instrument types, but they're obviously very advanced scientific experiments that have been developed over many, many years. and many of the instruments had similar counterparts on the Messenger mission. But the difference between the Messenger mission and this mission is that Messenger orbited in an ellipse that looked roughly like my cursor is drawing out at the moment, and was one spacecraft, and it had a really close view of the northern hemisphere and a much lower resolution view of the southern hemisphere, whereas Bepi with the 2 spacecraft will be able to completely cover north and south, and will have this sort of dual measurements of the system. Okay, so I think that's enough about spacecraft. So I just want to tell you briefly about our instrument, the Mercury Imaging X-Ray Spectrometer. It's the only UK instrument on board the mission, which was developed and built at the university by an amazing team of engineers and technicians. And, you know, I know they're not listening right now, but their ears will be burning. Here's a picture of them in their clean room gear, doing some of the final checks before, and this is the instrument you can see here, before the instrument was delivered to the European Space Agency. So the UK Space Agency is our lead funding agency, funded a good fraction of the instrument, but it's again also an international collaboration with a variety of universities across Europe. So even what we were doing in the UK, we couldn't have done it alone, but we are kind of ultimately, well, I guess I am ultimately in charge of the instrument, responsible for it, and all the data coming back and delivering that data to the European Space Agency. When I say it out loud, it's quite a daunting prospect. So there's 2 elements to the instrument, as you can well see. So it's basically a camera, but instead of it being a camera that's operating at optical wavelengths, it's operating at X-ray wavelengths. And it has 2 elements. One is the true imaging telescope, the circular optics here, and this is about 1 meter long, and the detector is at the back of the instrument. And then this instrument here doesn't do true imaging, but it's a collimator. So they're both spectrometers. This one does imaging and this one does not do imaging. And this is a collimator which has a very wide field of view, if you like. So you can think of this one as your kind of wide angle lens on your camera, and this one is the zoom lens. Doesn't quite look like it from that picture, but the zoom lens gives you the really fine detail, and this one will give us the global picture. But that picture will be at X-ray wavelengths. So there's quite a lot more I could say about the instrument, but I'm conscious of time, so I'm just going to sort of carry on forward, and if you would like to ask me about why I have a picture of a lobster at the end, then do come back and ask me that question. But one of the unique things about this instrument is the use of microchannel plate optics, which are the design and the optics, the little grey pieces that you can see on the front of the instrument there. And I know I'm biased, but I do think it is a rather beautiful instrument. I have to say, it's very, very nice space instrument to look at, and is literally gold plated, and the gold plating helps with you know, reflecting some of the heat from the sun, because that's a bit of an issue for us. Okay, so just to explain a little bit why we're using X-ray wavelengths, and that's because we are using a technique called X-ray fluorescence to work out what the surface of Mercury is made of. I'm just going to show you a very quick movie. It's just a few seconds long. This is the sun at X-ray wavelengths, and it's what you can see is the upper atmosphere known as the corona, and it's a source of very high energy X-ray photons, and those photons are always coming away from the sun actually, but not at a constant rate. Sometimes it's much more intense, and those are called flares. And so solar flares produce a large amount of X-ray photons and intense flares, and that really helps us with our data, and I'll explain that in just a second. But just to show you a quick movie of a solar flare going off, so you can see lots of filaments, and then wait, what happens? There it is. And so you can see this sort of solar flare event, and that's actually the detector of the instrument that's observing that is kind of saturating, because that X-ray flare was so bright from the sun. And we see those events from time to time. and we are more likely to see them at solar maximum. And that's really good news because Bepi is going to arrive at Mercury during solar maximum. So then what we do is we use the sun to actually study the surface. So the source of X-rays comes from the sun, and those X-ray photons then interact with individual elements on the surface of Mercury, and an interaction occurs whereby another X-ray, I won't go through all the details of this unless you'd like me to, but essentially what happens, X-ray fluorescence, you have the interaction of an X-ray with an atom, and it knocks an electron out of its shell. It then drops back down, and as it does so, it releases another X-ray. And that is the fluorescent X-ray that our instrument will measure. But the really neat thing is that released fluorescent X-ray that comes from this process then has a unique fingerprint of the atom that it has come from. So it has an energy which tells you exactly which atom is on the surface. So our instrument collects up these fluorescent X-rays coming from the surface of Mercury. We can use that information to tell us in great detail which elements are present on the surface. Okay, so I mentioned to you before that this circular side of the instrument is an imaging telescope. So what can we do? I mentioned 1 kilometre per pixel for the messenger images. So we have, with our collimator, our sort of resolution is simply the footprint of the instrument on the surface, if you like. So we will expect to get something like tens to hundreds of kilometres per pixel resolution. But with our imaging telescope, we're hoping to achieve a few kilometres per pixel X-ray images. So not as good as the visible images, but not much lower resolution. The best data we will get will be when we have those X-ray flares lighting up the surface. So we're kind of counting on the sun to help us out a little bit. Okay, very briefly then, I just want to say a few words about what we'll do with our instrument before I stop. It'll just be a couple more minutes. So obviously what we want to do is contribute to that question about how Mercury formed and evolved into the planet that we see today. Prior to the MESSENGER mission, there were sort of three main theories, only three theories for how Mercury may have formed. One is that the protoplanetary disk from which it formed was already sort of sorted in terms of its metal-rich content, and so the planet formed with a large iron core. But as MESSENGER showed, there wasn't any iron particularly on the surface, so that doesn't really seem to fit. Another theory is that there was a giant impact or a hit-and-run impact, and that impact, like the sort of thing you're seeing in the picture there, would have stripped layers off the planet, leaving behind this large iron core. And another theory again would suggest that extreme heat or extreme solar wind in the very early stages of the formation of Mercury could have evaporated off the outer layers, and that was another potential formation scenario. But in those two scenarios of giant impacts and extreme solar wind, we wouldn't expect to see volatiles on the surface, and we know from MESSENGER that there are volatiles on the surface in abundance. So we don't really have a good theory, or at least there are plenty of theories, but they don't fit the data, and that is really important. So we're hoping that our mixed data will help to give better understanding of this composition of Mercury to help contribute to the theoretical pictures which describe the formation of the planet. This is Caloris Basin again, now in glorious false colour. And I just wanted to point out that one of the things that we can do, and this gives you a sort of simulation here of what the mixed data would look like, the resolution of the mixed data would look like. So we're hoping that with large scale features, especially something like Caloris, we'll be able to get composition information actually across this sort of feature, which means we'd be able to differentiate between different craters and the various types of evolution that we see, including things like volcanic vents on the rim of that Chloris basin, and which elements are involved in that. We simply don't have the answers to those questions at the moment. A unique feature of Mercury are volcanic hollows, and this is exactly what you're seeing in front of you here, these sort of bluish, strange looking features which are found inside larger craters, and the process by which those are generated is not known. Intriguingly, it's possible that they're actually still being created, and one of the things that we want to know about is what chemicals and what atoms are involved in the creation of those features. So it's thought that there could be some volatile elements involved again, and we simply haven't had the ability with previous instruments to resolve those features inside the craters. So we're hoping to contribute to that. And then just one final thing I want to show you, skip through the detailed slide and go straight to the picture. One thing that we did find with the messenger data was that when we took the dark side, the night side data from messenger, we actually found an X-ray emission on the surface. And I just alluded to this a moment ago. Now, we wouldn't expect to see an X-ray emission from the surface from that process, which I described, from the sun's interaction with the surface, that fluorescence process, because the sun isn't shining on the night side of the planet. So where are these X-rays coming from? Our theory, which we have published, is that this X-ray interaction is kind of the equivalent of the aurora at the Earth. It's actually particles in the magnetic field of Mercury which are being accelerated and slammed into the surface of Mercury, guided by the magnetic field, and producing an X-ray emission on the surface. And again, that is completely new. There's no other example of that we know of in the solar system. And so we're really looking forward to being able to measure both these night side emissions, and when the day side is illuminated, we get our composition data. Okay. I don't know if you can hear sound or not. I probably didn't share the sound, so I expect you can't. That's just a little movie of the launch, which is always a very happy memory. I was very fortunate enough to actually go and watch the launch from French Guiana, which was incredible. And this is a picture of us at about, I think, 4 o'clock in the morning, after a very long evening of interviews and excitement and launch, and finally watching our instrument taking off from the launch pad and starting its long journey. So as I've said already, I know they're not here, but I always would send special thanks to the engineering and technical team for just the enormous amount of hard work and effort that it took for us to deliver this instrument. And members of the team have worked on this project for many, many years, more than a decade in some cases, and as such had to actually dedicated a significant fraction of their careers to this project. And without them, we certainly wouldn't be sending instruments into space. So as I said, it's now on its way, and we're very excited, but patiently waiting until 2025. So I think that is my last slide. So I will stop there. Sorry, probably talked too long, and feel free, if you have any questions, please let me know.
Emma, thank you for a fascinating and entertaining talk. Well, I'm sure there are lots of questions around. We have 34 connections tonight. So I'll ask you to put up a digital hand if you can. If you can't, wave at me, but give me time to scroll through the couple of screens I'm working with. So first up then, please, Andrew Devey, can you unmute your microphone, please? Thank you, Andrew.
Hi, Emma. I just want to say, brilliant talk, absolutely loved it. I particularly have an interest in the sun myself, so my question is involved the solar flares. Now, in the last solar cycle, we didn't have any super flares, and I noticed that Messenger was orbiting during the last solar maximum between 2011 and 2015. Yeah. So my question is, do you need to keep an eye on space weather, and is it like redundancy built into the spacecraft, or is it fully self-contained against such events?
That's a brilliant question. First of all, thank you. I'm glad you enjoyed the talk. Yeah, good observation about messenger. It actually, interestingly, the lack of solar flare events during that solar cycle was a bit of a detriment to the instrument like ours, the equivalent of our instrument that was hoping for a bit more activity. So I'm going to boast a bit about our wonderful instrument now, of course, because as you would expect me to do, but it is better. You know, I mean, it just is better. It's much more sensitive in terms of the actual energy resolution of the spectrometer. So if we were to have a repeat situation where we get to the peak of the solar cycle when Bepi will be there, and we find ourselves in a situation where there aren't many flares or flares strong enough to really light up the higher energies, that's what we're really hoping for, we still meet our basic science objectives. So when you write a case for an instrument, you have to sort of say what your science objectives are. And as you get deeper into that process of trying to justify someone to fund your instrument for £30 million over however many years, and you know, it's quite a lot of money, you have to say how you're going to meet those objectives and what the sort of contingency plans are, really. So the basic objectives are met. If we don't have a lot of solar activity, it will obviously be much better if there is. I hope that answers your question. Does that approximately answer the question?
Yeah, my fear was if we had an extreme event, like an enormous flare, because obviously with space weather, any alerts, you wouldn't have much time, but I didn't know if you got any redundancy to start powering things down or reduce power onto things.
I don't think it would. Well, it would upset the particle instruments. It would upset detectors. It could cause some issues. It could even cause damage to some of the detectors on optical instruments, for example, cameras. For us, it would just give us loads of data. In fact, so much that we wouldn't be able to downlink it all. We'd have to throw some of it out because we just wouldn't have the bandwidth to send it back. That would be unfortunate. But whilst we're just on this topic, obviously there are solar flares, which is what I've been talking about in terms of how that creates our data, which is very useful. But often with solar flares, you also get something called coronal mass ejections, which you've probably heard of as well. And those are slightly different. So the solar flares the effect is instantaneous because the X-rays move at the speed of light. And so the effect on the spacecraft is instantaneous. Whereas the CMEs are a release of magnetic field and solar wind plasma. And that moves at the solar wind speed, which is an unhelpful thing to say, about 400 kilometers per second. And so that takes a finite time to reach Mercury. So that might be something that would cause, well, it would be very interesting if we can measure the effects of something like that. We would expect it to have an interesting effect on Mercury's space environment. We might expect to see our X-ray aurora that I was talking about as well under those circumstances. So those are two different things that we would be looking out for. One, you don't get any warning of, in the sense that it's just instantaneous effect. But if you do see a large solar flare, there's a chance that we would also get one of those coronal mass ejections as well, which would be interesting. So we would hope that it wouldn't cause too much damage, but it could do.
Yeah, what I was thinking is, during messenger you got stereo A and stereo B operating, whereas I think they've lost stereo B now, haven't they? So you've not got the full 360-degree view of the solar activity. That was all. Yeah. Thank you for your answer. Excellent. Thank you.
Okay. Thanks.
Okay, Andy. Thank you. I'm looking around for questions again. Let me just cycle through. Whilst people are talking or thinking about questions, Emma, the political question about us coming out of Europe. Obviously, BepiColombo was in the pipeline before referendums and decisions, etc., etc. But up and coming missions, is it going to have an effect on British science?
Well, we sincerely hope not. Fortunately, there is a difference between our involvement in the European Union and our involvement in the European Space Agency. They are not the same thing. So we have been told. So I'm trusting that is indeed the case. We are, the way I normally describe it, the involvement with the European Space Agency is quite interesting how it works. It's run through our national agency, the UK Space Agency. And we effectively pay a subscription fee to the European Space Agency. So it's like a gym membership. It's nothing like a gym membership, but it's kind of like a gym membership. And then for your gym membership fee, you get things back. You get the use of the classes and all the gym equipment, and you can have a shower and all that stuff. So you get your return for your input of money, right? So we subscribe to the European Space Agency as a national agency. That input of cash, which is significant, I think hundreds of millions per year, that money then is returned to our country through contracts with the European Space Agency and through involvement in the missions. And there's no indication that that should change. So the contracts with Airbus, for example, and Kinetic that I've mentioned, the industrial contracts, they should still come back to the UK. And we should still be able to participate in missions, because that's what we're paying for with our subscription. So in that sense, I'm sort of hopeful and optimistic that nothing will change. Where there is some uncertainty at the moment is about our participation as individual scientists or teams in European research funding programs, and so that's is a very current issue actually, and the UK government have agreed that we can participate in those European Research Council programs, but it costs money. So again, it's an association fee this time, but I mean similar sort of thing. It costs quite a lot of money. So that is quite literally being negotiated probably as we speak. It's something that we're hoping will be agreed and firmed up and signed off very soon, which means we can still participate in those programs. So I'm nervous about that part, but the mission part and the involvement in space missions and the ability of UK industry to take part, we are pretty confident should not change.
That's all positive.
Yeah.
So that's really good. Peter Jarowalski. Peter.
Hi, Emma. Hi. Hello. Great talk. Thoroughly enjoyed it.
Oh, thank you.
I just have one question. How big a part of the mission is mapping the gravitational field of Mercury? I understand that the previous mission mapped it, for example, looking for mass coms and things like that. I understand, for example, as you go up the terrestrial planets, they tend to disappear for Venus and the Earth. For example, is that a major part of the mission? Mapping?
Yeah, absolutely. So the thing that I mentioned quite briefly, which is the improvement from the previous mission about the orbit, really, again, that will make a significant difference for measuring. Obviously, there's measuring the gravitational field, but what you're looking for are those smaller deviations away from a sort of standard picture. It's a bit like the magnetic field as well. You're looking for what we call higher order terms in those fields, gravitational field or magnetic field, that can tell you about sort of interesting features in the mass distribution or what have you, and how the planet, how the planet's interior is distributed. And that, of course, is a big question, because it's very hard to measure. And hence you use the gravity field and the magnetic field to help you with that. So yes, is the short answer. It is a significant part of the mission. And in fact, I always sort of joke about this with my colleague who runs that part of the instrument team, because it isn't really an instrument. You sort of get it for free. He would not thank me for saying that, because it sort of implies it's no work, which is not true. But you do sort of get it for free, because you get the gravitational field information from the it's very clever actually. It relates to the Doppler effect and how the planet actually affects the spacecraft as it flies close to the planet, and it slightly perturbs the orbit, and those changes in the predicted orbit, which obviously is sort of, obviously we hope we know to enough of an extent that we don't mess up our mission, but those little variations, very small variations, then actually Doppler shift the radio signals between the little spacecraft back to the Earth, and you can measure those variations in the frequency of the signal, and that gives you your change in acceleration, which is then due to the gravitational variation. So it's a pretty neat thing. And Jupiter behind me has a spacecraft called Juno orbiting around it at the moment, and even from the distance of Jupiter orbit, you know, and with the accuracy, it's the same people actually, exactly the same guys, Italian guy runs the gravity experiment on Juno and is running it on BepiColombo as well. So it should be a significant improvement on the messenger data.
Wouldn't you expect that, for example, for smaller bodies like the Moon compared to Mercury, that they are lumpier, for example, and less evolved internally?
It's a good question. I think the biggest thing for Mercury really is this question about the scale of the iron core, the fact that it has a magnetic field, which implies it has some molten element to that. And so if you have a molten element to that, then you have a sort of differential motion potentially. Yeah. So those are the kinds of things that we simply don't have a good handle on in terms of data from Mercury. So the gravity team would be much better people to give you more detail. Yeah, I think that's the basics of what we hope to get from that.
Thanks. I read, if I could just finish up, I read somewhere, maybe just going off Jupiter, the gravity data, I think Juno, everyone expected there to be a solid core in Jupiter Centre, but that's apparently not the case. Apparently it's all mixed up.
Apparently it's like a slush puppy.
Density tends to go down towards the centre, if I'm not mistaken, something like that.
Yeah, it's pretty complex. Jupiter is, it's I'm trying to think of the terminology they use.
Differentiated?
No. They came up with something, I can't think what it is now. There's something like mush balls. Do you remember reading that? It's some strange thing about the fact that there's sort of like a snowy interior. I mean, some strange cartoon. Fascinating. Basically, Jupiter does nothing that we would expect. It always throws us a bit of a curveball.
Oh, thank you very much. Thank you.
Okay, thank you, Peter. Peter Lloyd.
Yes, thank you very much, Emma, for a very fascinating talk. I was particularly struck with the brief period when you were talking about the surface of Mercury and its obvious similarities with the Moon. And you talked about the blue areas, areas of low reflectance. And my immediate thought was, can those be basaltic lavas just as they are on the Moon? But then, of course, you went on and talked about obvious lava flows and ghost craters and all these sort of things. And as a result of the Apollo missions, of course, we know the composition of various ones of these lavas, and we know their reflectance spectra. And I wondered whether BepiColombo has sufficiently acute spectrometers on board to make that sort of measurement, or whether in fact your X-ray spectrometers will do that job, or
Yes, brilliant question. And also making those comparisons between the composition measurements that we have at the moon and then comparing those with the data that we get from Mercury is also something that we can do. And taking samples of rocks or analogues and using ground equipment to sort of create spectra that we can then compare with our data when we finally get it. So as you mentioned, our instrument is going to be looking at the elemental composition. So we will only be able to measure individual elements on the surface. So it's a chemical composition. There is an additional instrument, which I didn't mention, which is a thermal infrared spectrometer. And so they will be able to get composition in terms of the mineralogy on the surface as well. So actually, if we put our data together with the infrared data, then I think we'll be able to get a much better handle on that, on those materials. The low reflectance material is an interesting one. The messenger team towards the end of the mission, I think I'm trying to just remember now, I think it was towards the end of the mission, they had some observations which were suggesting that it could be carbon based. Now, unfortunately, so like graphene or some, graphite type surface, low reflectance material. So that's of course an interesting question as to whether that could be possible. It could be a very old crust that has been made visible by impact craters, and it's sort of dug down into the subsurface layers of the planet, and potentially that's what we're seeing when we see that low reflectance material. But for us, and I know that the Bepi team are really keen for us to say that we can measure carbon with our instrument, but unfortunately the energy that we would need to get down to is actually at the lowest range of our instrument. So we're being, very cautious about getting anybody's hopes up that we can do that measurement. And actually it depends on how our instrument survives the cruise, really, as to whether it can perform well enough at those low energies in order for us to be able to extract carbon from our signature. But well, that's all I can say about that at the moment. I hope we can, but we were not getting anybody's hopes up.
I mean, presumably that's another volatile that you're not really expecting to see, although you say you have seen other volatiles.
Exactly. It's really curious, and I think I think lots of people always give Mercury a bit of a hard time as being one of the more boring of the planets, but actually I think what's been revealed by these missions is that every planet has its own unique set of circumstances, and none of them are the same, and they all have interesting features, and Mercury has thrown us more questions after the messenger mission, thoroughly justifying our return there with a new mission, of course. So plenty for us to do.
Yeah, and presumably Mercury was probably molten at some point in its early history. I mean, the fact it's differentiated would rather imply that. And of course, the Earth was similarly molten at one time, and yet it has huge amounts of volatile on its surface.
Exactly. So those comparisons again are very important, aren't they? It's it is important to, in my opinion, and as you can tell, I study a variety of planets, so I like to make those comparisons between the different bodies and try to fit that into a kind of overall picture that helps us to understand planets in a more general sense. And I think when we're listening to results about planets in other solar systems that we cannot measure, like we're measuring Mercury or Jupiter or Saturn, because we can't go there, but our missions within the solar system, actually sending a spacecraft to the planet to make those observations, can help us to understand extrasolar planet systems as well.
Well, thank you very much. Yes.
Pleasure.
Thank you, Peter. Emma, During the flybys, the Mercury flybys, will there be a chance to test or get data back from your instrument?
Another great question. Unfortunately, not from our instrument. If you go to the Science Museum in London, you will see why. So basically, our instrument is just smack bang next to the Mercury transfer module. So our instrument is just looking down at the transfer module. So we cannot see out at all. So we can't make any measurements, sadly. Well, we can take detector measurements, but we can't use the optics until the separation has taken place. But other instruments can operate. So there was a Venus flyby. When was the Venus flyby? October last year. Last year was a weird year, wasn't it? October last year, there was a Venus flyby, and some of the instruments were operating and able to take some measurements at Venus. There's another Venus flyby coming up in August, and then the first Mercury flybys. So the instruments like the magnetic field instrument can operate, and an instrument which measures solar activity, which we actually work with, that can operate, but sadly not ours. So we have to wait until the mission begins.
Okay. So I think what we will do, we've worked Emma really hard tonight. So can we give her a big maximum spent in Astronomical Society? Thank you. Thank you very much, Emma.
Thank you so much. It's great to see you all.
Thanks
for listening.